So today we're going to be talking about bonding. There are many theories of bonding. The one that we will be using today is called Lewis dots, in honor of Lewis. And this is the simplest bonding theory. There are other, like valence bond and molecular orbitals, which are more sophisticated, and we'll look at those later. So we'll start from Lewis. And when we talk about the term Lewis dot structures, we refer to either elements, Lewis dots, or compounds, Lewis dots. Elements we've done. When we talk about Lewis dots of elements, specifically representative elements, we need our periodic charts out, and any element in group representative, meaning group A. Any element in group 1A, like lithium, sodium, potassium, have one valence electron. Lithium will be 2s1, sodium will be 3s1, potassium will be 4s1, so the valence, the outermost electrons, are represented by dots. So any of these group 1A, lithium will have one dot, sodium will have one dot, potassium will have one dot. What about group 2A, beryllium, magnesium, calcium? How many dots for these guys? 2. So we put 2 dots. Beryllium is a 2s2. Magnesium is a 3s2. Calcium is a 4s2. Representative. So we skip the transition. These guys are transition. These are not representative. Group 3A, like boron. How many dots for boron? 3. So you can put them like that. What about carbon? Group 4, how many dots? 4. This, fluorine. Group 7, how many dots for fluorine? 7. So you go and put your 7 dots, one in each side, and then start pairing them. Group 8, with the exception of helium, the noble gases, these are a complete octet. These are the happy guys. So neon will have 8 dots. Argon will have what? 8 dots. Anybody in group 8? Okay, so the number of dots for representative elements, we look at the group number, and the dots is equal to the valence electron, which is the group number. Group 1, 1 dot. Group 2, 2 dots. Group 3, 3 dots. That's step 1. Then we move to Lewis dots of compounds. And in compounds, we first recognize whether the compound is ionic or whether the compound is covalent. And if it is ionic, like what? NaCl, we do a Lewis dot structure in a totally different manner than if the compound is covalent, like what? CH4. Okay, so if we have a metal and a non-metal, we by now know more than that. We really look at the electronegativity values, and that's our criteria. But in general, we have said metal and non-metal, the electronegativity values are going to be so different because they're on opposite sides of the chart that electrons are going to be transferred. So you have ions of sodium, ions of chloride, positive, negative species, as opposed to molecules. So ions versus molecules is a concept that's not new to us, and that is fully going to be put in use now. So if we are asked to do Lewis dot structure, step 1, find out if it's a compound, whether this compound is ionic or whether it's covalent, because our approach is going to be totally different. If it is ionic, sodium, element sodium, group 1 had 1 dot, but ion sodium lost that dot. And it doesn't have any dots. Where did that dot go? To the chlorine. So chlorine is group 7, element chlorine had 7, but ion chlorine has a -1. So if it is Lewis dots for ionic, we need to write charges. +1, +2, +3. Let's do another ionic. If I have Lewis dot structure for magnesium chloride, and you know the formula for magnesium chloride by now, hopefully. What do? Okay, magnesium is a metal. As an element, a minute ago we saw magnesium is group 2. So if we look at the periodic chart, magnesium is a group 2 element. And as a bachelor, it used to have 2 dots. Cl as a bachelor used to have 7 dots as an element. But now, this is not what's happening. The 2 dots of magnesium were lost. Okay, so magnesium's electronic configuration as an element and as an ion is 2 different things. Magnesium +2 is isoelectronic with who? Neon. Okay, so magnesium lost 2 electrons, so everybody here is going to be a +1. Everybody here is going to be a +2. Do we remember this? Everybody here is going to be a +3. So magnesium that as an element used to be a 1s2, 2s2, 2p6, 3s2. Those 3s2 valence electrons are lost. And by losing them, the core 2s2, 2p6 makes magnesium +2 isoelectronic with neon. So magnesium is a +2 ion, and Cl is a what? -1. Again, Cl is a non-metal. Non-metal are going to be negative ions. So Cl -1 is isoelectronic with argon. So Cl gains 1 electron from 7 valence, picks 1 up, but since magnesium is donating 2, you need 2. Okay, so each Cl is picking 1 up. But if you have 2 Cls, okay, so the bookkeeping is we have only 1 magnesium and we have 2 of this guy. We don't write it like this. This is what we mean. This is just too ugly to put as a formula. This is exactly what is meant by this. But if 2 electrons are lost, we have a deficit of 2 electrons, and 2 electrons are picked up, the sum of the oxidation numbers give you 0. So this right here is the Lewis dot structure for magnesium chloride. We write, it's a combination of the Lewis dot of the elements and the formula. Okay, so we do what we did for the elements, and then remove electrons if it's an ion, a metal, +1 if it's a group 1 ion, +2 if it's a group 2, like magnesium, calcium, group 3, like aluminum, it will be a +3. And the non-metals will pick 1 if it's a group 7. Group 7, picking 1 up gives you 8. Group 6, like oxygen, sulfur, selenium, will pick 2 to make it to 8. So the octet rule has been applied and obeyed. Okay? If it's aluminum oxide, what's the formula for aluminum oxide? Al2O3. Okay, so what's the Lewis dots for aluminum oxide? Aluminum, we look them up in the chart, it's a metal. And it's a +3. And oxygen is a group 6. It's 6 valence, and it wants to pick up 2 more. So these guys will pick up 2. Fluorine, chlorine, bromine, pick 1 up. Nitrogen will pick 3 up. Aluminum is a +3. Beryllium, magnesiums are +2. Lithium, sodium, potassium are +1. So we're using the periodic chart in an effort to dissect what's happening in this compound. So aluminum ends up as a +3 ions, and we have how many of them? 2. And oxygen instead of having 6, which had as an element, it has a 7th and an 8. So it picked 2 electrons coming in -2. Sulfur will do the same thing. Selenium will do the same thing. Any group 6. So how many oxides do we need? 3. So what are we saying? We have 2 aluminums, aluminum number 1 and aluminum number 2. This is what we say, what we mean. This is not what we write. And we have oxygen number 1 with 8 electrons. Oxygen number 2, they all turn as oxides with 8 electrons. Oxygen number 3 with 8 electrons. So we lost 6 electrons, we gained 6 electrons. Every electron has accounted for. This is the Lewis dot structure right here of aluminum oxide. Okay, so we are transferring electrons if you have an ionic compound. Ionic compounds transfer electrons. The metal loses electrons, and the nonmetal gains electrons. If we don't have an ionic compound, if we have a covalent compound, and the example you just gave me was CH4, remember that hydrogen for us is a nonmetal. So if you have now 2 nonmetals, how do we do this? Covalent compounds. Covalent compounds, they share electrons. Nobody wants to lose electrons. Metals want to lose it, but nonmetals, when they combine, neither one. Okay, so we're looking at, again, our periodic chart, and if we're looking at nonmetals, we're looking at group 7, like fluorine, chlorine, bromine. Group 6, like oxygen, sulfur, selenium. We're looking at group 5, these are the nonmetals, like nitrogen, phosphorus, arsenic. We're looking at group 4, like carbon. We're looking at group 3, like boron. Okay, and we say, okay, boron has 3 as a bachelor, carbon has 4 as a bachelor, nitrogen or any group 5 has 5, oxygen or any group 6 have 6, fluorine, chlorine, bromine, they all have 7. And now they're going to combine. And hydrogen, it's at the other end, under group 1, has 1 dot. So if I have 1 carbon and 4 of these in CH4, okay, so if I am going to do the Lewis dot structure of CH4, and H is a nonmetal, and carbon is a nonmetal, I have a covalent compound. And that's criteria number 1. And once I know it's covalent, I share it. So I draw the most symmetrical structure. And for CH4, I have 4 hydrogens, so I'm going to draw them around the carbon. And then I look at the dots for carbon, look at the dots for H, meaning I'm looking in the periodic chart what group they are, the representative elements. And every hydrogen has 1 dot, so it shares it. And I'm going to write a red dot. And every carbon has 4 dots, so I am going to share those 4 dots. So I'm going to have 1, 2, 3, 4. I have 4 electron pairs, and every electron pair, according to Lewis, is a covalent bond. So this is the Lewis dot structure for methane. It has 4 covalent bonds. Okay? Are we okay? So 1 electron pair equals a bond. We also had looked at the shape of CH4. This is the shape of CH4. The carbon would be the black ball in the center. You have one hydrogen bonded. The orange and the green are in the back. Those are hydrogens. And there's another hydrogen coming forward. So it's not flat like my original drawing indicated. It's a tetrahedron. If we connect these, every angle is 109.5 degrees. Okay? 90 degrees, which is what this looks like. This looks like 90 degrees. 90 degrees is too close. Electrons are negatively charged, so these are not 90 degrees. This guy is sticking out. These guys are going back. And these are all tetrahedrons. 109.5. Okay, if we have NH3, go, NH3. Nitrogen in the middle, how many hydrogens? 3. Let's do the hydrogens, electrons white. Red. And the nitrogens, you can do, if you don't have two colors, just do pencil and pen. Nitrogen has how many dots? Okay, so we look at the chart. Any group 5 has 5 dots. Nitrogen is one of them. So I'm going to give 1 to the hydrogen, reciprocating. That took 3, 4, and 5. So now I have how many covalent bonds? 1 electron pair, another electron pair. So every electron pair is a bond. Is this thing up here a bond? No. What's that called? A lone pair. So do I have a tetrahedron? No, I really have a pyramidal structure. Okay, so I have this guy sticking out, these two guys towards the back. So it's like a little Egyptian pyramid. Okay, so I go back to my tetrahedral, and now I don't have the white one. Now I don't have the same structure. I have a nitrogen in the middle. And I have 3 hydrogens, and this is a huge lone pair. That's squishing these angles from 109 to 107 degrees. Because I have a big negative section. Besides, nitrogen is more electronegative than hydrogen, so these hydrogens are going to be slightly positive. Okay, so I have 107 degree angles. My black one is now nitrogen. My green, orange, and red will be my hydrogens. And I don't have this guy. I don't have a hydrogen up there. I only have 3. That would just be the stick without the white. The white is representing a lone pair. So that shape is pyramidal. That's like a little pyramid. And it's a triangle in the back, so it's called trigonal pyramid. What about if I have water, H2O? Draw the most symmetrical structure. That's step 1. And then check above the group number, the dots. Oxygen is group 6, so it has 6 dots. Hydrogen is group 1 and has 1 dot. So I draw the most symmetrical structure, and maybe this is what comes out. Hydrogen has how many dots? 1, so we always start with hydrogen. Always. If hydrogen's in the picture, start with it. Share it, the one and only electron it brings. And oxygen continues. It has 6. 1 for this hydrogen, 2, 3, 4, 5, 6. So in all of these, we have achieved an octet. Carbon has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. So the octet rule is being applied, it's being obeyed, and according to Lewis, an electron pair as a bond, and as soon as you come up with 8, you have a noble gas electronic configuration, you've achieved a very stable configuration. So how many covalent bonds do I have now? I only have 2 hydrogens. And that's going to be a lone pair here. And that's going to be a lone pair there. So if we go back to the tetrahedral structure, now I have an oxygen. I don't have 3 hydrogens. I have 2 lone pairs. And you can put the lone pairs wherever.
The angles will be on yourself.
The angles are going to be even smaller. So it went from 109 to 107 to 105. It's not really 109, it's 109.5. It's not really 105, but 104.5. But if you remember 105, that'll be good enough. Okay, so now these 2 guys are above, and these 2 guys are below the plane, if you could visual that one. Okay, so I'll show you a model. This is my tetrahedral, carbon, HHHH. If I remove 1 hydrogen, that's ammonia, nitrogen, HHH. 1 lone pair, and these angles now are not going to be 109, but this guy is squishing them more, so it's 107. And if I have water, I have oxygen in the middle, and these is the negative section. This is squishing these guys a little more because negative repels negative. Okay, so I have 2 lone pairs in water. Water is not linear like my original drawing could have implied. It's V-shaped. Okay, so the models help. This is my angle, 105. Okay, so this is my angle. Oxygen, hydrogen. Do you see? The models really help. Okay? Okay, so 1 electron pair is 1 single covalent bond. So in here I have 2 covalent bonds. And what? 2 lone pairs. And the shape is what? This is what I see. I see my oxygen, hydrogen, oxygen. It's V-shaped or angular or bent. The angles are there, 105. Okay, so remember 109, knock it down 2 degrees, 107, knock it down another 2, 105. Water is not linear. Okay, so in here, when you first draw it, if the water was linear, there would be no life on Earth. No life on Earth. So these things, we're going to have a lot of corollaries, a lot of layers laid on top of. So 1 electron pair, according to Lewis theory of bonding, 1 electron pair forms a single covalent bond. What about 2 electron pairs? A double covalent bond. What about 3 electron pairs? A triple covalent bond. Okay, so we had CO2 last time. Let's do CS2. Is CO2 and CS2 any different? No, why not? Because oxygen and sulfur are both what? In the same group. So I can have CO2, CS2, CSE2. They're all going to have 6 dots here. Oxygen has 6 dots, so does sulfur, so does selenium. Okay, so, and when I say carbon, I could have said silicon. I could have said germanium. Any of these could be central atom, and they all bring 4. So make your patterns. Okay, if I have CS2, first draw the most symmetrical structure, and then check for your valence electrons for each element. For each element. So, and this one was a little funky, so we used a different method. We snapped it. You remember the word snap? You snap an answer. There is no P. The S stands for share. This is what you need, and this is what you've got. What have you got? this is what you've got. This is reality. Carbon has 4. Sulfur has 6. This is what's available. This is what's available. They all want 8, but that's what they've got. Okay, we may want millions of dollars, but we don't have that necessarily available in our bank account. Okay, so this is the big one. What do we put between the carbons and the sulfurs? And again, this sulfurs could have been oxygens or selenium, any group 6. This guy, instead of carbon, could have been silicon or germanium, and the Lewis dot would be identical. Okay, so what do we need? Everybody needs 8. Sulfur needs 8, this guy needs 8, and that fellow needs 8. So 8 times 3 is 24. What do we really have available? Carbon has available 4. This guy has available 6. And that guy has available 6. So we pull out our charts. We're looking in the charts. And carbon has 4. Sulfur has 6. Each of the sulfurs have 6. So 6 plus 6 is 12. Plus 4 is 16. So it's 6 plus 6 plus 4, 16. And when I subtract these two, what I need minus what I have, I need 24 and I have available 16. I share what? What's 24 minus 6? 8. So I'm going to put 8. 1, 2, 3, 4. 1, 2, 3, 4. Sharing is where my angle's going to be. Where my sharing, where my electrons are bonding the carbon with the sulfur. That's the glue that keeps these people together. Okay? Do I have any lone pairs? No. Okay, so when we're talking about lone pairs here, and again, there's 2 different types of questions when I ask about lone pairs. The lone pairs that I'm referring and I'm making a big deal of is to get to the shapes. Okay, we're squeezing in lone pairs in the central atom only. This guy, carbon, has 4 electrons to the right, 4 to the left. This guy had 4, and now he has 8. Good. But what about these sulfurs? How many do they have? They only have 4. This guy so far has 4, and so far has 4. So they haven't achieved the octet. And I have shared 8, but I really have available a total of 16. So I have another 8 available. Of the 16 that I have available, I have used 8. So I have 8 more. And I'm going to use them for the sulfurs to complete their octet. So the whole idea is to make 8 for every element. And if this sulfur has 4, it needs 4 more to make it to 8. And if this sulfur has 4, it needs 4 more to make it to 8. And I don't care where you put them. But this thing right here is my bonding. You can't double it. You have to only do one line so it won't get erased. So that's 2 electron pairs. So what is that? 2 double bonds. What shape do you think this guy has? If carbon has a negative cloud repelling another negative cloud, these are my electrons floating in there, and my sulfurs are here. What shape do you think this fellow is going to be? Linear, because this guy repels each other, and they're going to want to be as far apart from each other as possible. So if the central atom only has 2 regions of electron density, I don't care if it's a single bond or a double bond or whatever, it's negatively charged region. An electron density is negatively charged. That repels the second electron density that's negatively charged. If one's pointing east, the other one's going to be pointing west. If one's pointing north, the other one's going to be pointing south. So from Lewis dots, we're adding shapes. Last time we only did Lewis dots. I'm piggyback writing shapes. And again, in 1046, this is day 1. So keep your notes for 1046. This is an important topic. There's many, many other concepts that are going to be in here. The other one that we did last time was N2, Lewis dots. Draw Lewis dots. for N2. And let's go ahead and snap it. Share is what we need to know. Is needed minus available. Let's check what they've got available. We go to our little periodic chart. Periodic chart's out. Nitrogen is group 5. It has 5 dots. So that's step 1. The elements dots is step 1. The drawing the most symmetrical structure in this case is trivial because I only have 2 nitrogens. The shape of this guy has to be linear. Between 2 points, I can only have a straight line. You can make a triangle with 2 points and patent it. Okay, so the shape is silly. Any diatomic molecule, N2, O2, F2, whatever, they're all linear. Those are only 2 elements. But I want to know how many electrons are here. What is the bond? That's the bond that keeps one nitrogen glued to the next fellow nitrogen. How many do I share? That's what I share. Everybody needs 8. So I have 2 people that need 8. I need 16. And what's available? 5 for each nitrogen. That's 10. What's 16 minus 10? 6. So I am going to share 6. So that's what the snapping does. It tells you the bond. And that's a big one. Because if you know that if you got a triple bond and every nitrogen needs 8, I've shared 6, but I do have 4 more to go because I have available 10. Are you with me? Any questions? Okay, so I have 4 more, and in order for them to complete an octet, this nitrogen has 6 and 2 more is 8. This other nitrogen has 6 and 2 more is 8. So this is a what? A triple bond. 1 triple bond. Okay, so 3 covalent bonds is not a triple. 3 covalent bonds was NH3. This is a covalent bond and another covalent bond and another covalent bond. That's not a triple bond. That guy is pyramidal. Okay, but N2 is linear. CO2 is linear. Yes. There's no central element. Okay, so if I ask you what's the shape for N2, that's a silly question. If that's in your test, hey, start with that one. There are, okay, we only talk about lone pairs to determine the shape. Okay, in the test, there are going to be 2 types of lone pair questions. There's going to be a lot of shapes questions. And in order for you to determine shapes, and we're going to talk about electronic geometry and molecular geometry, is the central atom. Okay? But if I'm talking about a different kind of question, like how many bonding electrons and non-bonding electrons, how many lone pairs in total of the molecules, then I want all of them. Okay? But that's a totally different deal. Like, in a minute, we're going to talk about formal charge. And the lone pairs are going to be part of that. Okay? But the big deal with lone pairs is to determine shapes. Okay? And it's the central atom that's determining where are the other angles going to go. Okay? Somebody had asked me that in an email. I get so many emails. And that is a good question. So I'm pointing out central atom lone pairs today. Most of the time to get to shapes. And the next module, module 11, is all shapes. That's all central atom lone pairs. But you will have questions that you have to count. You know, like if they ask you how many bonding and non-bonding. Okay, so in here you have 6 electrons, and these are bonding, and these are non-bonding electrons, the lone pairs. Okay, so that's a totally different deal. So are we okay up to there? Not done any ions, not done any funky people. What's this fellow's name? SO3? Okay, so I'm going to do sulfur trioxide. Thank you. We're learning it. I love you. Yes. As opposed to this guy. What's this fellow's name? Carbonate ion. He's an ion. Has a plus or a minus charge. If it's an ammonium ion or a sulfate ion or a carbonate ion, these guys have extra electrons. Okay, or a deficit of electrons. These are ions. So let's go there. These we haven't really done much. Let's start with these. Enough of a review. So we go to SO3. Where do we have Lewis dot structure of? Same question. Lewis dot. We know that these are not ionic. None of these are ionic. When I talk about a carbonate, that's an ion, but the bonds between carbon and oxygen, those are not ionic. Those are covalent bonds. They're sharing electrons. You see the difference? Okay, so the whole compound may be sodium carbonate, and that's an ionic compound. Or I may have ammonium hydroxide. That too is an ionic compound. But these are all covalent. They're sharing because the oxygen and the carbons, the nitrogen and the hydrogens, the sulfur and the oxygens, they're all non-metals. So we're sharing what they've got available in an effort to make it to 8. That's all this little game is about. Okay, so SO3. Anybody got it? Do we snap it? How many people? I have sulfur and 3 oxygens. I have 3 oxygens that need 8, but I have a sulfur that also needs 8. So I have what? 4 elements that need 8. So I need what? 32. What do I really have? I have 6 there, and 6 and 6, that's 18. And another 6, that's 24. So I have 6 electrons, and I have 4 elements that have 6. So what do I share? I share 32 minus 24. I share 8. How do I share 8? I'm going to remove these little 6's. I'm going to rewrite this. O, 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 S. I share 8. I'm going to call him oxygen 1 and 2 and 3. All the oxygens are the same. I'm just trying to make a point. So if I need to share 8, I can go 1, 2, 3, 4, 5, 6, 7, 8. Or I could have done what? One, 2, 3, 4, 5, 6, 7, 8. Or I could have done what? And this is oxygen 1, 2, 3. 1, 2, 3. I could double bond sulfur with oxygen 1, or double bond sulfur with oxygen 3, or what? Double bond sulfur with oxygen 2. In all of these structures, I'm sharing 8, am I not? So the sharing is the bonding. The sharing is the important part. The sharing is the whole chapter. This chapter is about bonding. Okay, but let's pretend we just did the first structure. And I shared 8, and I have available 24. So I gotta make an octet. None of the oxygens have an octet. Sulfur's very happy. Sulfur already has 4, 5, 6, 7, 8. Sulfur's done. Sulfur achieved the octet. So I'm counting 1, 2, 3, 4, 5, 6, 7, 8 electrons for sulfur, and this guy is ever so happy. But none of these oxygens is happy. They're not happy because they haven't had their octet completed yet. So what do? I continue to count from 8 all the way to 24, giving everybody 8. Okay, so let's go. 8, done with the sharing. 8, 9, 10, 11, 12. I've accommodated 12, and now this oxygen has 8. 13, 14, 15, 16, 17, 18. Now this oxygen has 8. 19, 20, 21, 22, 23, and 24. Now this oxygen has 8. So you continue, look at your available electrons, the valence electrons that are going to be shared, to give an octet to everybody. And just like I did it for that one, I'm going to call that structure 1. That's hybrid structure 1, which is just as valid as if I would have double bonded oxygen 3 with sulfur. Whoever has a single bond needs 8 more, needs 6 more to make it to 8. Whoever has the double bond needs 4 more. And we do call that structure 2. And now I'm going to call it structure 3. So whoever has the double bond, I've shared 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So I am going to have 3 hybrid resonance structure. And this is a new one. Which ones are they? Structure 1. I had a double bond here. Single, single, and everybody else had an octet. Structure 2. I had a double bond up. And everybody had an octet. Structure 3. I had a double bond here. Whoever has a double bond needs 4 more. Whoever has a single bond. Okay, so this structure is as valid as that one, which is as valid as that one. Okay, so when you have more than one way to represent a Lewis dot structure, you introduce a new concept. Ozone, O3 has resonance. Carbonate has resonance. Okay, so all these other structures will also bring the same. I know, you're asking me, how do I ask this in a test? I can ask you, does SO3, or I give you a bunch of compounds, and which ones of the following have resonance? So you do Lewis of all of them and find out which one has this type of pattern. Okay, so I really have a double bond and 2 singles. I have kind of like a double bond moving from oxygen 1 to oxygen 2 to oxygen 3. Now let me ask you, what kind of shape do you think this guy has? How many regions negatively charged around the central atom do I have? So I'm looking at the central atom. That's the guy that's directing the bonds to my peripheral elements, the ones outside. So I have 3 negative clouds. That's it. I don't have any lone pairs. What shape do you think can 3 negative clouds take if they want to be as far apart from each other as possible? Trigonal planar. So I have a triangle, a good equilateral triangle. And the angles in any triangle is what? What are these angles? So between any oxygen, sulfur, oxygen, I don't care if it's that one or that one or that one, the angles are 120. 120 plus 120 plus 120 gives you 360. So this guy is triangular, or triangular planar because it's flat. Okay? NH3 was not planar. NH3 was a little Egyptian pyramid because it had a lone pair. That central atom had a lone pair that was also negative center that repelled the other bonds. Are we getting the point? Yes, we are getting the points. Okay? We said we were going to do... Okay, so I don't need a model to show you that flat piece of paper is fine. Nobody's sticking out of the screen, in front of the screen, in back of the screen. Do carbonate. That's an ion. Lewis dot structure for carbonate. Draw the most symmetrical structure. Bum, 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 bum. And now I have an extra 2 electrons. That's what this fellow is telling me. So if I'm snapping it, share is needed minus available. I have available 2 more than what the elements are bringing. Are we okay? Are you with me so far? How many people need 8? 1, 2, 3, 4 elements need 8. So I have 4 elements that need 8, so that's 32. What do I really have? I have 6 and 6 and 6 for the 3 carbons. That's 6 times 3 is 18, plus 4 more is 22, and the 2 extra ones, I have 2 extra, so I have available 6 plus 6 plus 6 plus 4 plus 2. 4 plus 2 is another 6. Let's divide it, maybe, not. Plus 4 plus 2. So I have available 24. So again, 32 minus 24 gives me what? Same thing as I had. Same thing that I had a minute ago. In here, I got another 8. And I had the same skeleton. Instead of having a sulfur in the middle and 3 oxygens, I have a carbon in the middle and 3 oxygens. And I need to write brackets -2 because I am dealing with a carbonate ion that has 2 extra electrons. But I'm going to have same deal as before. A double and a single and a single, or a double here and a single and a single, and a double here and a single and a single. Wherever there's a double, I put 2. So after a while, we begin to see that we can do patterns. We can do this very fast if we do lots of homework. Examples. Okay? Yes?
So we can use the extra 2 elements.
Extra 2 electrons? Anywhere.
They don't belong to
Anywhere. Yeah, in the next chapter, when we do acids, like when I go H2CO3, that's no longer an ion. That's carbonic acid. Okay, then it's an oxyacid. An oxyacid, this is what you're going to do. Your hydrogen is going to be bonded to your oxygens. That's what oxyacids are. And the hydrogens, it had a red electron sharing it. Okay, so that's another way to do it. You always give the extra electrons to the most electronegative elements. In this case, hydrogen would be bringing those 2 extra electrons. That's where the carbonate got the -2 from the 2 H pluses. Okay, and then you go same deal. Double, single, single. Ta-da, 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 ta-da. Okay, so you're going to put the 2 extra electrons out, the most electronegative element. But it does, in this particular case, it doesn't matter. Give them anywhere. Any other questions? So if that fellow SO3 was triangular, carbonate is also going to be triangular. Carbonic acid is going to be triangular. And the angles here are 120. I need for you to see the pattern. Don't just get an answer isolated and think there's so many different cases. It's the same thing. Chunk them into similar patterns. It's called learning. And we're going to do NH4 plus. And we snap it. Share is needed minus available. Everybody needs 8. I have, you're going to tell me the shape of this guy after we're done drawing the Lewis dot structure. Just by drawing patterns. Okay. What do we need? The nitrogen needs, this guy needs 8. But the hydrogens, do the hydrogens need 8? No. This guy needs 2, and this guy 2 more, and 2 more, and 2 more. Okay, so I need 8 and 8. 16. Are we okay with the 16 that we need? That's what we need. But what do we have? Nitrogen has 5. Each hydrogen has 1. And I have a deficit of 1 electron. So it's plus 4 minus 1. A deficit of 1 if it's a plus 1. A deficit of 2 if it's a plus 2. Just like a minus 1 has an extra 1, and a minus 2 has an extra 2, and an extra 3 for a minus 3. So 5 plus 3 gives me 8. So what do I share? 16 minus 8. I share 8. So if I share 8, I'm going to go a bond here, a bond, and a bond. That's 2, 4, 6, 8. So after a while, you don't need to do dot, 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 dot. Every electron pair, every dot, dot is a bond, a covalent bond. So what shape do you think this guy's going to have? If the central atom has 4 negative clouds, 4 bonds coming from it. Thank you. I'm going to have my nitrogen in the middle, so now my black ball is my nitrogen. And it doesn't matter where I put my white or red or green or blue. They're all 109 degrees apart from one another. Okay, so now I have my nitrogen on an H up and 2 H's back, because that's as far as they can go from each other. And the whole thing needs to be shown in brackets with a deficit of 1. And the angles are 109.5, just like, who else had this structure? Tell me. CH4, who else could it be? If I don't have a carbon, what do I have? A silicon. Very good. H4. Who else would have this structure? Carbon, silicon, germanium, group 4, H4. What about if I don't have hydrogen? Fluorine. Very good. Carbon and 4 fluorines. Or it could be carbon and 4 what? Fluorines. Or it could be carbon and 4 what? Bromines. Or it could be carbon and 4 what? Iodines. Or it could be silicon and 4 what? Fluorines. And it keeps going on and on and on and on. And we're learning patterns. And if they all have the same Lewis dot, guess what? They're all going to be tetrahedral. They're all going to be 109 degrees, just like ammonium ion. Are we getting it? Are you with me? Okay. Let me go back to SO3, sorry, and do something else. I'm assuming that we know how to do Lewis dot of SO3. Yes, we've done SO3 and carbonate and many others, and this was it. Now I'm going to introduce another term. Okay, so we introduced resonance with SO3. But if I am going to be nice and go and say, okay, this is the structure of SO3, and I know of these distribution, oxygen brought 6, right? So every oxygen, I'm going to write the oxygens in blue and the sulfurs in red. If oxygen brought 6, oxygen 2, these two were for oxygen. So these 2 must have been coming from where? From the sulfur. And if this oxygen had 6, 2, 4, 6 was oxygen. And these 2 must have been who? Sulfur. And these 1, 2, 3, 4, 5, 6 must have been sulfur. Okay, so now I'm classifying. Okay, so that was a distribution. But who gave what, really? And sulfur was very nice. He treated oxygen 3 to a bond, to a covalent bond, like you're treating somebody to dinner. And sulfur treated oxygen 2 to a covalent bond. Oxygen didn't chip in anything. He had 6 and he kept all 6. Greedy fellow. That is called a coordinate bond. Okay, so that right there, we translate it into this right here, and I am writing a red arrow. And what does that red arrow mean? That bond is there because sulfur, buena gente sulfur, contributed with an electron pair of its own, and oxygen didn't chip in anything. So those are coordinate bonds, as opposed to the way we started. You know, when you started here, hydrogen shared electrons with carbon. Hydrogen chipped 1, carbon chipped 1. So that was an electron pair, but each element contributed with 1. Do you see the difference? Okay, so to determine that type of answer, if this question is in your test, you can first snap it, get your distribution, but then go back and say, okay, who had what? And oxygen had 6, and sulfur had 6. So then you dissect of all those dots who belonged to what. What bond was here, what bond was there. Another concept, formal charge. After you do lots of examples, you're going to get patterns like if carbon's in there and it's a covalent compound, carbon is going to form 4 bonds. It could be 4 bonds to hydrogen, like you had in here. Carbon, hydrogen, 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 hydrogen. That was CH4. Or it could be a double bond and 2 singles, or a triple bond and 1 single. So after you do a lot, you're going to say, hey, you know what? Carbon always forms 4 bonds. And those things are going to just expedite your answers. When you recognize different elements always doing the same thing. Oxygen is always going to form 2 bonds. It could be 2 single bonds, like in the case of water, or it could be a double bond, like in the case of CO2. Okay, so you're going to begin to draw lots of patterns. So when you are asked for a question like, what is the formal charge of blah, 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 blah. And I'm just going to assume we've done lots of homework and we know how to do Lewis. So I'm on page 11.6. I'm doing formal charge, and I'm giving you the Lewis dot structure already. The Lewis dot structure is really your bookkeeping of electrons. This is an ion. And the Lewis dot structure came out to be like this. Okay? And now we're going to talk about bonding electrons, not shapes. Okay, so for this particular topic, I'm not after shapes. I am after answering what is the formal charge of. And I'm going to call this guy carbon number 1, and I'm going to call this guy carbon number 2. And this element, hydrogen, I'm going to call him third element. Okay? The rules for assigning formal charge, they're just that, rules. You are going to find out formal charge of carbon number 1, formal charge of carbon number 2, formal charge of hydrogen, which is element number 3. And this is all you do. you first look at the group number. What is the group number of carbon? Carbon, 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 carbon. Where's carbon? Carbon is group 4. Carbon, silicon, germanium, they're all group 4, has 4 valence electrons, 4 dots. So that's step 1. This guy, group number 4. The second carbon is 4, hydrogen is 1. Okay? Then I am going to look at my bonding electrons. Bonding as opposed to lone pairs. Lone pairs are non-bonding. Okay? So now, if I had this structure, I must have had dot, 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 dot. How many electrons did I bond here? I bonded 6 electrons. Well, I'm going to take, for those 6, 3 belong to him and 3 belong to him, right? So I'm going to take half. So it's half of the bonding. Half of the bonding electrons. So instead of 6, I'm going to write what? 3. And I am going to add or subtract, because it's minus times a plus, all of the non-bonding electrons. Okay, so if I have a lone pair, how many non-bonding electrons is that? Okay, non-bonding electrons, meaning lone pairs. The electrons in a lone pair. In a lone pair, well, how many electrons do I have there? 2. Okay, so it's 3 plus 2. Non-bonding electrons are these guys. These are my 2 non-bonding electrons. So what do I have? 4 minus 5. What's the formal charge there? A negative 1. What about carbon number 2? Let's follow the same rule. It's just a rule. Group number 4. Half of the bonding. 1, 2, 3, and 4. Okay? And lone pairs, none. So formal charge, 0. So this guy has no lone pairs there or there. Okay, so whenever I have a triple bond, you'll go dot, 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 dot. Whenever I have a double bond, go dot, 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 dot. Whenever I have a single bond, just go dot, dot. Okay, so that's half and the other half by half. Let's do it for the third element, hydrogen. Group number 1, half of the bonding, 1, and no lone pairs, so the formal charge there is 0. If I add the formal charge of all my elements, which is minus 1 plus 0 plus 0, the sum of my formal charge, sum minus 1 plus 0 plus 0, and I get the charge of the ion, because this was an ion. That was a very amazingly great Lewis dot structure. Okay, so sometimes I'm going to draw Lewis dot structures and they're going to be crazy and they're not going to be logical. When do I have a logical? So this is a way to check your Lewis dot structure. Okay, so you come up with a Lewis dot structure, you do your snapping, you do your this and your that. And if the sum of your formal charges of all the elements equals the charge of the ion, that is a valid formal charge. Okay? We have finished module 11, guys. Study so hard. We are continuing with shapes on Tuesday. Have a wonderful day.